And with that, I would now like to formally begin today's conference and introduce Andrea Copping.
Thank you. Good morning. I'd like to welcome you to this Annex 4-sponsored webinar on environmental research in marine systems. Today's topic is the effects of energy removal on physical systems. Could you go to the next slide, please? We have 3 presentations here today. Our first presentation, I'm going to introduce all 3 speakers now, and then they'll hand off to one another. Our first presentation is by David Wolf. David is a associate professor of marine physics at Heriot-Watt University, which is part of the Highlands and Islands University group in the UK. Dr. Wolf studies physical interactions that occur due to the removal of marine energy within marine systems. He uses modeling techniques and remote sensing tools. His other research interests include the physics of the air-sea interface, climate, and global climate carbon cycle. Dr. Wolf will be talking to us about the implications of tidal resource interactions. Our second speaker, Xiaoqing Yang, is a senior research scientist at Pacific Northwest National Laboratory in the U.S. As a physical oceanographer, Dr. Yang studies interactions of marine energy devices with the environment, and he also looks at a broad range of hydrodynamic interactions, including storm surge and sea level rise. And Dr. Yang's presentation will be on the extraction of tidal stream systems for a sustainable environment. Our third presentation will be given by Sandia National Laboratory personnel. Kelly Rule will start off. Kelly researches interactions of marine energy devices and marine systems in the U.S. Dr. Jones focuses on sediment management, riverine and coastal systems, and interactions of marine energy and offshore wind devices with the environment. And Kelly and Craig's presentations will be on effects of wave energy converters on wave and sediment circulation. Now I'd like to turn this over to my colleague, Luke Hanna, who will be facilitating the rest of the webinar. Luke?
Yes, thank you, Andrea, and good morning to everybody and good afternoon. The only other thing that I would like to add is that, as Colin mentioned, we will be taking questions from the participants after each presenter. So once you have a question, please type the question in the top box at the top of your screen. And then we'll hopefully have time for further discussion at the end of all the presentations. So with that, I'd like to turn it over to David Wolf.
Okay, my name is David Wolf, and I'm speaking from late afternoon in sunny Scotland. As the title suggests, I'm going to talk about some of the implications that arise from considering tidal resource interactions. I'm going to talk a little bit about the modeling methods we use, but only just a very little. Just to credit a few people, some of the modeling I'll show was done by myself with a student when I was at the University of the Highlands and Islands by the name of Matthew Easton. And some other results I'll use to illustrate what I'm talking about are by another research group and by Scott Draper and colleagues. So to just explain what the structure of the talk is, I'm going to go through some motivation. Then I'm going to describe the modeling interactions, modeling approaches, and the various types of interaction you can get, sort of a new classification of interactions, and then move on to talking about some of the implications, including the policy and management implications of those interactions. So to start with motivation, I'm going to think about this both from a point of view, if you like, of a greedy engineer trying to get as much resource as possible from tides, and I'm also going to think about it as an environmental scientist. So as far as the engineer who wants to get as much energy as he possibly can out of the tides, there's some important things to know about. Basically, because the tidal system is quite complicated, as soon as we start trying to take energy from it, stuff changes. And one of the first conclusions is you can't just take a model of one site, calculate how much energy you can take, and then model a different site and add those all together. you have to consider it as a system. And that makes life a little bit complicated. The optimum is not obvious and requires experimentation. On the other hand, as I'll explain, if you think about it in a simple way and use simple models, there are some rules that are actually really very simple indeed. The most simple one can be just summarized by the phrase parallel is good, serial is bad, which refers to how you arrange things in channels or systems of channels. Move on and think about it as a sort of an environmental scientist. Again, where you put stuff is important, but you have to remember that not everything related to the tidal development happens locally. So a lot of people who are looking at the environmental effects think about things that are happening locally. They're thinking about things like displacement and collision, and they can go about looking at that in a very simple way with global information systems. Simply spot where things are happening in the same place and decide whether those two things can happen in the same place. Other things, and the fluid dynamics is not the only thing, you get effects at a distance. So you might have to worry about, for instance, migration of fish. So you don't have to consider just where you're fishing, but where those fish pass through. But the most important one of those is the fluid dynamics. You have a very complicated situation, and it makes the whole problem of spatial planning a little bit tricky. So I'm going to talk about some fairly simple modeling approaches, and I'm going to start by talking about the sort of model that most people use when they try and predict what a specific proposal would do to the hydrodynamics, and then talk about a much simpler approach, which quite a lot of people have been using, but not nearly as many as used at the hydrodynamic models. So this is an old-fashioned model with what we call a structured grid, and it's a nested grid, so you can have a fine mesh for a local area, which is the area in red there, which is just lots of fine red squares, and the area in blue is a broader mesh. That's a reasonably successful approach, and similarly you can down use unstructured grids, which basically put the resolution where you most need it. All of these models are sort of limited domain models, and that raises a problem with looking at tides, because we have what we call the open boundary problem, which is essentially an insoluble problem. A much simpler way of going about it is if you think about the labor involved in setting up a grid like this and doing a separate run for each possible development, it's hard work. A much simpler way is to break it down as an analogy to an electrical circuit. So this is something I've looked at for the area of local interest to me near Orkney, where you have Pentland Firth, which is one of the world's best known potential tidal stream sites, and it's adjoining a large natural harbour called Scapa Flow and various channels and sub-channels. So my cartoon visualization of that is something like that, where you're representing what's going on by resistances, inductors, capacitors to describe the fundamentals of how that flow will go. In this presentation, I'm going to go to something a lot more simple and just think about resistances, and I'll get on to that in a minute. If you want to know about the slightly more complicated one and why you would use capacitors, for instance, that's a reference to a paper. So if we think about how you represent things, we're going to look at a few cases, and I'm going to break down interactions into three types: what I call systemic, which is basically what's happening beyond your local domain, and what I call interchannel and interchannel effects. So as far as interchannel effects, we have a very good example of some very good calculations that have been done both with, if you like, a traditional 2D model and with a circuit diagram approach. And this has been published by Scott Draper and colleagues in 2 papers. And what they considered is the maximum extractable energy depending on putting essentially tidal fences at various places within Pendle and Firth. And that allows you to look at the interactions between those. So if we look at those interactions, the effects are really rather dramatic. One reason they're dramatic, which is not wholly realistic, is that what we're looking at is the maximum energy you can take out. So these effects will be smaller the less energy you take out, but nevertheless this is quite instructive. And what I must emphasize about these arrows, the black arrows is the amount of energy you get, and the green and red arrows are the difference with respect to the base case, which is where you develop only one subchannel. So I'll just remind you where subchannel B is. It's called the inner sound of Stroma and Pendle and Firth, and it is indeed probably the most advanced development in the local area. So to emphasize, what we're looking at here is the energy you get at B. So additional to this may be energy you can get from the other sites, but this is the energy you get at B, depending on whether it's occurring alone or in concert with other developments. And what you discover is if you just develop B, you can get, in principle, a fairly hefty amount of energy. But if you start adding a development at C or at D, or both C and D, let me go back and see these. So you're basically helping to partially block or hinder flow through these other subchannels. You will get much more energy at B. On the other hand, it's not all good news, because if you develop up here, E, that looks like it might not interfere with the flow through B at all. But if you do the calculation, you discover that you will reduce the amount of energy at B by developing B. So this is where the whole idea of developing parallel channels being beneficial, but avoiding developing developments in series, even where they don't look like they interfere, they probably do. How we can represent that is we can think about really the simplest circuit representation. So this is something called a Norton equivalent circuit, where the rest of the world is represented as a current source and an impedance, and then we just think about these, in this case, just two simple channels, and we consider the channel where we're developing, which has a natural resistance R main, and our development is essentially adding a new resistance, a load resistance RL, and meanwhile there's another channel with the bypass. And we can understand pretty much what goes on just in those simple terms, that if you increase our bypass, it helps to keep the current in the main channel high, and you can take more energy out of it. So it's not really necessary to attach stuff to the grid in a bypass. What's important is you're increasing its resistance. You're discouraging flow in that bypass channel. Now that's clear, but you can sort of represent these sort of separate channels as separate bits of the circuit. What we've also done a little bit of experimentation is to what extent you can think about two parts of a channel or multiple parts of a channel in the same race. So we know most channels will not have full width tidal arrays, so what will happen? So this is based on some modeling, again, of the inner sound of Stroma, where we didn't assume that there would be a full width array across this inner sound, but we assumed the array would be concentrated in the middle. So the dark lines here are where the array is assumed to be, and then we have in blue areas where the current is reduced in average by adding that array, and red where it's increased. And there's a lot of complexity here that cannot possibly be described by the simple model. What you find is that broadly this is what you would expect just from thinking about it as a simple circuit, but some of the flow is diverted to the sides. The flow through the array is greatly reduced, partly as a result of that diversion, and partly because flow is also diverted, is blocked entirely through that subchannel. And again, you basically can use exactly the same representation to get a reasonable idea of what have the intra-channel effect. So if we think about this both from an engineering point of view and an environmentalist point of view, is if we compare what you would get for a full width array with a partial array, this kind of puts us off doing a partial width array, though that is pretty much what every proposal on the board is at the moment. But if we do a full width array, then we will have a smaller reduction in flow, we'll get plenty of energy, and we won't have that big an environmental effect in terms of the flow speed. If we do a partial array, what we find is in the part where we put the array, we get a very big drop in current. And in the part where we don't have the array, in what we call a bypass, you get an increase in current. So in a way, you get the worst of both worlds. You're getting very large changes in flow in both cases. Okay, so what does that mean in terms of planning arrays? Well, first of all, think twice about partial width arrays, and is there a way around having that? How do you maintain a good energy yield, given that in reality no array is ever going to totally cover a channel? And we can also think about how you make planning decisions about where developments happen. And I'm going to do that very quickly, just sort of a quick rush through lots of possibilities. So I've got this set up as jurisdiction A and B, and that's in a very loose sense, but we're assuming on one side of a channel, person A is making some decisions, or group A is making decisions, and on the other side of the channel, a different group is making decisions. And we'll start by thinking maybe they won't be talking to each other, but maybe they should. So the white is the actual waterway, the channel, and I put two islands in just to make it an interesting theoretical case. So we may have proposals to develop these 4 sites, which look like sensible places to put tidal arrays, and what were the consequences of choosing any permutation of these 4 proposals? Well, basically, some permutations are pretty good and some are pretty awful. So if we just think about that, first of all, just think about it in terms of this equivalent circuit idea in the simplest possible way. So I've got one resistance, it's the natural resistance, which is always there, and we're thinking about adding this other resistance for each development and thinking about what that will do to the flow. So if we just think about what will happen if you do develop just one of these, so the bottom left one in this case, how good is that? Well, it's probably not very good, and the reason is if you develop that one site, this is what the change in the flow, the trend in the flow will be. Basically, you will push more flow along where the blue arrows are and away from where your development is. Basically, you're allowing the flow to divert around the site where you want the energy. If we carry on and consider another case where on one side of the water they decide yes for both, and on the other side they decide no for both, well, that really is truly awful, because pretty much all the flow will go around and you won't get any energy, and you'll also have really strong flow down here with potential environmental effects. So this is another one where they both say yes, but they do so on different ends of a channel. And that, again, is not going to be great, because the flow is going to go through there, or more of the flow is going to go through there. On the other hand, if you do something like this, where they both agree to look at the left-hand, to develop the left-hand end of the channel, so we're adding resistance here and here, but not here and here, then that's good. You'll basically, you will get some reduction in the flow, but you're not doing any massive diversion of flows. So that's the basic idea. So that's all based on believing that you can do a really very simple representation that tells you something useful. And I'm not here to tell you that these models are perfect, but I'm also happy to point out that basically all models are wrong, which is the quote here. And what you're really looking for is useful models. And in my opinion, electrical circuit analogies are very useful both for explanations, as I've done today, but also for serious research. But you're able to consider a very large permutation of possible developments quickly before you move on to trying to do anything more complicated and more time-consuming. So these are part of, if you like, a diversity of models we should be used. As far as more sort of general implications about how we think about taking energy from tides, I think we do have to think about tidal interactions and realizing we're messing with a complicated system. And for instance, we may think that if we don't develop a particular place, well, nothing's going to happen there. Well, that ain't true, because first of all, somebody might be developing somewhere else, and anyway, the whole world's changing anyway. So we shouldn't confuse undeveloped with unaltered, and we shouldn't confuse just simply being inactive with conservation. But sometimes you actually have to actively manage systems in order to achieve your ends. And from a policy point of view, I think there's a strong case for not letting developers develop where they want and just telling them not to interfere too much with each other. You probably have to design a system from scratch, which is going to meet your strategic ends, and then invite developers to implement part of that strategy. Okay, thanks very much. I'm going to leave a slideshow for now, and if anybody wants to ask me some questions on note, hopefully I'll be able to see that.
Very good. Thank you very much, David. That was excellent. Okay, so our next presenter is Xiaoqing Yang with the Pacific Northwest National Laboratory. Xiaoqing, if you want to go ahead.
Okay, thank you, Luke. So, good morning and good afternoon. Today I'm going to talk about tidal energy extraction for a sustainable environment from a modeling perspective. Okay, so Nexus Line. So we all know marine and hydrokinetic energy include energy captured from tidal currents, wave, and ocean current. Okay, and today I'm going to focus on the effect of tidal energy extraction. Numerical modeling is a very effective approach in terms of support MHK energy development, especially to assess resource characterization, quantify the practical extractable energy, and also assist device siting and array optimization. More importantly, numerical model can be used to evaluate the potential environmental impacts, such as system flushing time and also biogeochemical process in the system. Okay, next slide. So actually, David briefly mentioned about the overall modeling approach, which includes structure and unstructured modeling, and vary from 1D to 3D models. Okay, so the modeling approach we take in PNNL is to use a three-dimensional finite volume coastal ocean model. It is one of the state-of-the-art model, and it is based on unstructured grid framework, which we think is important for the tidal energy to development because we do need a high resolution in the area of tidal farms. So FVCOM simulates tidal hydrodynamics, wave and current interaction, and it also simulates water quality and sediment transport. So to further evaluate the extractable tidal energy using numerical model, it is important to actually include the tidal turbine effect in the model. So we developed a tidal turbine module in FVCOM using a momentum sink approach. Basically, we include additional term, a sink term in the momentum equations, okay, and solve the equations. And the tidal turbine module embedded in FVCOM will allow us to simulate the extractable energy by different configurations of tidal turbine, okay, and also to evaluate the effect of tidal energy extraction on the physical systems. Next, I'm going to show you a couple of applications of the model, specifically include idealized tidal channel and the base system, and also to a real-world site in Puget Sound. Okay, next slide. So this is a slide for simulate a flushing time in the channel and the base system with a tidal turbine arrays deployed in the narrow channel. This is a very typical, system, in most of the study sites, because the tidal channel usually has very high tidal current speed. Okay, so the idealized tidal channel we set up here is with realistic dimensions listed in the table. For example, the length is about 30 kilometers, and the width is 6 kilometers, and the water depth is 6 meters. And the tidal turbine module include a number of input parameters. Okay, it include the number of turbines you can specify in each cell or in a series of numerical cells. And also you can specify the tidal hub height and turbine diameter and the thrust coefficient. You can also specify the drag coefficient associated with the foundation and the supporting structures. Okay, and to simulate the flushing time of the system, what we did is we fill up the bay with dye concentration, and we deploy different number of tidal turbines in the channel and run the model. And this animation basically shows a dynamic process how the dye is being flushing out of the system. Okay. So next slide. I'm going to show you how the energy extraction from the tidal channel would affect to the flow rate across the channel, and in turn to affect the flushing time of the system. Okay, so when we take out energy from a system, especially in the tidal channel like that, we will reduce the flow across the channel. That's a common knowledge. But how much? That's the important question. Okay, very commonly people will talk about the maximum theoretical extractable power, but in reality that's impossible. Okay, so if you look at the left image, that you can see as we increase the tidal energy extraction, it will also increase the flow rate reduction, okay, by percentage. And the increase in flushing time will be an exponential function of the energy extraction, okay. However, if you look at the low flow reduction range, actually we can pretty much approximate the flushing time as a linear function of the flow reduction. However, one thing we need to aware is the increasing in flushing time actually is much higher in terms of a percentage than the flow reduction. So for this particular case, for example, it's about 4 times greater than the flow reduction because of energy extraction in the tidal channel. Okay, next slide. So other environmental variables of interest include stratification, okay, if we look at salinity and the temperature in the system, and also the two-layer circulation, which is important for the water exchange or renewal of a bay. And other water quality variables include dissolved oxygen. So if you look at the upper left image, it shows the mean surface salinity with and without tidal turbines. So with the tidal turbine in place, you actually will see an increase of surface salinity because it increased the mixing when you deploy the tidal turbine in the system. Okay, so it's basically reduce the stratification, increase mixing, and in turn you have a higher salinity at the surface. Similarly, actually you also see a reduction in the mean surface velocity. Okay, so it actually reduces the two-layer circulation. Okay, and of course that will result in the increase of flushing time. On the right image, it shows a system-wide average of the difference of surface and bottom dissolved oxygen as a function of time. This is actually a 1-year simulation. We have sorry, my computer just went to sleep. Okay, so the right image shows the dissolved oxygen comparison with and without the tidal turbine. Okay, and we can see that with the tidal turbine in the system, and the dissolved oxygen difference between surface and the bottom will be decreased. Okay, it means actually you're actually mixing more of the dissolved oxygen in the system. But in turn, it's also reduced the flushing rate of DO, okay, in the system. So let's move to the next slide. Next, I'm going to talk about application to the Tacoma Narrows in Puget Sound. So Puget Sound is one of the top priority sites for tidal energy development in U.S. Okay, Tacoma Narrows is at the very bottom of Puget Sound, which connected to the South Puget Sound. And Tacoma Narrows is about 1,500 meters wide and about 40 meters in depth on average. And it has a very high tidal currents. It's about 3.5 minutes for the maximum flood current, and the very large tidal range is over 4 meters. And as I mentioned before, we use a unstructured grid model. So to simulate the tidal turbine in the channel, we actually reduce the grid cell size, okay, from about 200 meters in the ambient area to about 30 meters, which is about in the same order of tidal turbine diameter. Okay, next slide. So we will look at 3 different configurations in the system in this experiment. So with the 20 turbine farms and the 50 turbine farms and also 100 turbine farms, the configuration of this tidal turbine farms with a tidal turbine diameter of 10 meters, and the turbine hub height is 10 meters from the seabed. Okay. Of course, if we increase the tidal turbine diameter, of course, the energy extraction, because we know the energy extraction is the proportional to the area of the sweeping area, so it will be much greater. For example, if it's 20 meters in diameter, it will increase by 4 times of energy extraction. Okay. So next slide. So this slide shows the extracted power with the tidal turbine farms I showed before, with the 20 and the 50 and the 100 tidal turbines. And we can see this is particularly in Puget Sound. Okay, we see very strong variation over a spring and the mid tidal cycle. Okay, so even though we have a very strong tidal currents, we have to be aware that during neap tide we actually have the current is much smaller. Okay, so if you look at, on the right panel, it shows the springtime and also the neap tide, and you can see springtime is much stronger during when we extract the tidal energy. So if you do tidal average over the extractable power, and you can see the power outputs are nearly linear proportional to the number of tidal turbines in the turbine farms. Okay, so this is especially true when we consider relatively small number of turbines and also extract a small amount of tidal energy relative to the maximum energy in the system. Okay, next slide. So now let's look at the far field and the local or near field effect of tidal energy extraction on the physical system, especially the South Puget Sound, which is behind the Tacoma Narrows. Okay, so the left panel shows the tidal amplitude deficit, which means the difference of tidal amplitude for M2 time only with and without the tidal turbines. Okay, so in this case, we actually see very small change in terms of tidal amplitude. It's only about 0.3 centimeter reduction in tidal amplitude, and the reduction in the flow rate actually is less than 1%. Okay, so the far field in general, when we look at it as a system-wide, it's small. However, if we look at the local effect, it's measurable, even with 20 turbine farm. So if you can look at the vertical profiles and at the 50 meter depth, which is about 10 meter above the seabed, there's up to 15 to 20 centimeter per second difference at because of the tidal turbine in place. The color contour shows the bed shear stress deficit because of tidal energy extraction. So even for a 20 tidal turbine farm, which is relatively small tidal turbine farms, we see a strong difference in terms of bed shear stress. Okay, so that has the implication on the sediment scour and the transport. Okay, so next slide. So this is my summary slide. Okay, so integrated modeling is an effective approach to support the MHK energy development, in particular to assess the accurate resource characterization and to assess the system-wide and the local effects of tidal energy extraction, and also to assist device siting and array optimization. It is also important to consider the potential environmental impact in connection to tidal energy development, such as circulation and flushing time and other biogeochemical process and the transport. That's all of my presentation. Thank you.
Great. Thank you very much, Xiaoqing. That was great. So we do have one question from for both PNL and Sandia National Laboratories, who will be presenting next. Will PNL or Sandia be pursuing any work in quantifying the extractive effects of deep ocean current energy converters as well?
No, we haven't done anything on the ocean current energy extraction, but the model actually we developed actually is suitable to address that. For example, in the Gulf Stream, right? We can apply to the model to address those similar issues, but we haven't done that.
And this is Jesse from Sandia. I just wanted to chime in that the modeling techniques are very capable of doing that study, but at the present time we're not focusing on ocean current energy.
Yeah, but the concept is the same. Okay.
Concept is the same. Okay. Thank you. And Xiaoqing, were the same flush times and energy extraction relationships observed at other model scales?
In other model scale, you mean? I'm sorry.
At other model scales, were the same flush time and energy extraction relationships observed at other model scales?
I'm not aware of that. So.
Okay. And then one last question. Can you provide more information on how you set momentum sync for a tidal turbine?
Yes, actually, in my slide, there's a reference on that. So there's a detailed description of how we implement the momentum sync terms to simulate the effect. So I can share that slide.
It's in your slideshow now?
Yeah, you can just move back. I mean, probably, let me see. Yeah, the 5th slide. And I think this slide will be made available to all the attendants, right? So.
Right, yeah, so these slides will be posted on TGIS for the TGIS knowledge base for later viewing. So was it the 5th slide you said, Xiaoqing?
Yes. So it's published in 2013 in the Renewable Energy.
Okay, great. Well, thank you, Xiaoqing. Our next presenters are Kelly Rule and Craig Jones. And so I will, I guess I will turn presenting rights over to Kelly. Is that correct?
No, over to Craig, please.
Okay.
All righty, Kelly, I think we should be up.
All right, thank you. All right, I'm going to be presenting today on the effects of wave energy converters on wave and sediment circulation. I'm going to start by giving an introduction and talk a little bit about the numerical code development. And then I'm going to pass the presentership role off to Craig, who's going to talk about some of the applications of the model in existing domains. Can you go to the next slide, please? Thank you. All right, so the motivation behind this work is to better understand the potential environmental impacts of deploying wave energy farms, referred to as WECs, in real environments, to understand their impact or potential impact on wave propagation and circulation patterns. The potential impacts are changes in the sediment transport, ecological processes, and socioeconomic services. So the big motivation behind this work is that wave energy converters haven't been deployed in arrays before, and we have to rely heavily on numerical codes to be able to evaluate the environmental impact. So numerical tools such as SNL Swan that we've developed are tools that are used to assess this potential impact. These can be used to inform the environmental assessments that can be used for the permitting process that's required in the U.S. Next slide, please. So the objective of this work is to develop and evaluate a numerical modeling tool called SNL-SWAN that we have developed here at Sandia that I'm going to talk about, and then Craig is going to talk about the simulation of wave propagation through hypothetical record to perform model sensitivity analysis and examine the effects of wet characteristics on near and far field wave conditions, and to also evaluate the changes in sediment transport patterns. Sorry, the transitions on my slides here are a little bit slow. Okay, so past studies on modeling wave energy converter arrays have been done with the open source code called Simulating Waves Near Shore SWAN. This is an open source spectral wave model that was developed by TU Delft. And the way that WECs are modeled using this code is as what's called a constant transmission coefficient with KT. And what that does is it extracts a constant amount of energy across the whole spectral domain within the SWAN code. The governing equation for that is shown on the right-hand side. So the KT term is just a ratio of the Lee wave height to the incident wave height, and that doesn't really capture the whole energy extraction properties of wave energy converters. So what Sandia has done has modified the open source code SWAN, which we call SNL-SWAN, to include a WEC module that better models wave energy converters. The way we've done that is by defining a WEC power, defining the WEC power performance as that the user can define in terms of a WEC power matrix or a relative capture width curve. These two options were chosen because these are typical metrics that developers use to quantify the power extraction of their device. The power matrix is defined in terms of a peak period and a significant wave height, whereas the RCW curve is just a function of the incident wave period. And what it does is define the amount of energy that's extracted for each of those different C states. Next slide, please. So within the code, what that means, I don't know if anyone else is experiencing this delay, but it takes a while for my slides to transition. Okay. There we go, I can see it now. So what that means within the code, if you want to focus on the top right-hand figure, is that if your incident spectrum is the black line, constant energy extraction would be the red line, so it's going to have the same spectral shape as the incident spectrum, whereas if you account for the frequency or period dependence of the WEC extraction, you actually end up extracting more power at certain period bins than others. And so that's shown by that green line. So in this case, that's using a relative capture width curve that's defined by the blue line. And so what this means is that with the WEC module, we can better understand how the device actually performs at the site and its impact on the spectral shape and wave propagation. And Craig's going to talk a bit about some of the applications of this. On the development side, we've performed some code verification and validation by comparing the changes that we've made to SNL-SWAN to similar codes developed by the University of Exeter and Oregon State to check that we are predicting the same, or at least on the same order of magnitude changes, and also by comparing the extracted plus the remaining spectra power to be able to reproduce the incident power spectrum. An example of that shown on the bottom left. So we've been able to do some preliminary validation of the code as well by comparing the predicted energy extraction from the WEC within the SNL-SWAN code by comparison to an experimental data set that was provided by Oregon State University and Columbia Power Technologies. These were tests that were done in 2010, 2011, and we've been able to use this data set to check the wave height reduction and the spectral shape change that the code is predicting versus was observed in the experimental data set. And so what this does is allow us to have some confidence in the near and far field changes that we're seeing in the wave shore environment, which Craig is now going to talk about.
All right, thank you very much, Kelly. So Kelly and her colleagues at Sandia developed this great tool to look at what happens in WEC arrays with the deployment of a WEC array. So our goal was really to scale this, and how do we apply this at a site to really look at what the effects are at a site. And so similar to what David and Zhao Qing had shown for the tidal energy converters, we're essentially doing the same thing with WEC arrays. So we used a site in Monterey Bay, California, which is central coast of California, off the coast of Santa Cruz. And we were leveraging that effort with a lot of field studies that were done for the Department of Defense, Department of Energy, and also for some local municipality concerns as well. So we had a very good data set with which to validate the model with. And one thing we like to emphasize is, especially with these near-shore models, is that we have very complex circulation in the near shore, so making sure we have the baseline correct is one of our first steps. And then with that baseline, we can compare what happens when we put a WEC array in place. And here's an example map of the region. This is the city of Santa Cruz. We deployed hypothetical WEC arrays on about between a 40 and 50 meter deep contour, which is about where many industrial entities are looking at deploying these arrays. And then we had an array of 20 points that we observed inshore of this. So we could look at the changes in wave height, the changes in wave direction, period, any spectral changes as well. So our general approach was we wanted to look at 8 different types of WECs. And a paper by Bob Barrett et al. in 2012 did some numerical benchmarking studies to look at how some idealized WEC devices would behave, how much power is expected to be absorbed by these devices, and generally what the power matrix of these devices are. If you look on the upper left-hand side, these are similar to the power matrices that Kelly had shown earlier. The color here is the power absorbed as a function of significant wave height on the y-axis and period on the x-axis. And as Kelly had mentioned, this is not a constant linear function over the entire spectra. This varies over the spectra. So we can apply the relative capture width curves that Kelly had shown into SWAN for each of these different devices to approximate and model the effects of these devices. So we had a number of different sizes of arrays from 10, 50 to 100 WECs, and in that 40, 50, and 60 meter zone looked at different spacings in depth as well. And then looked at different WEC spacings of 4, 6, and 8 diameter spacing. And generally most developers are talking about at least a 3 to 4 diameter spacing. And so if we look here on the bottom right-hand side, the oscillating water column, this is a 50 meter by 24 meter footprint device. So the spacing is in excess of 100 meters between these devices. Whereas a heaving buoy on the left-hand side, which is 20 meters, is again 80 meters between devices, up to an 8 diameter spacing, just to give you a sense of scale that we're looking at here. So when we run from some of the normal conditions offshore Santa Cruz, and this is a specific example of a condition that would have the most impact on the nearshore zone. So it's a southerly swell that happens in the summertime. And here what we see are 4 different configurations from the upper left-hand corner a 9.5 meter oscillating flap to on the lower right-hand corner the 50 meter oscillating water column that we were looking at. So you can see the relative difference in size and spacing of these arrays. And what we're looking at here is a % difference in wave height. And as you'll notice, these scales change on the right-hand side from 0 to 10%, all the way for the 26 meter oscillating flap, which is a very large bottom oscillating flap, up to 30% reduction in wave height in the direct lee of these devices. So this gives you an idea of what some of the patterns look like and what some of the results of our sensitivity testing looked like. So if you recall, we had 18 points here in the inshore of the devices. And if we look at the results in terms of those, we can plot up all those results, and we'll look at as a function of device type, and actually we're going to normalize that in terms of power, but we're looking at the percent difference in wave height. So here on the x-axis we have the different types of devices, and then we have the actual yearly average power absorption of each of those devices, from 2 kilowatts all the way up to 225 kilowatts for the large bottom oscillating flap. And as we can see that you have a direct correlation between the power absorbed and the effect on the wave height. So again, it's a somewhat logical conclusion, but now we can start to look at that as a function of devices deployed and where they're deployed. We can also look at the number of WECs. And of course, as we expect, the number of WECs increases, we have the percent height difference increases. So you have more WECs out there, you reduce wave height more. But if we normalize that by the kilowatts absorbed, again, that starts to become a relatively constant function. And then finally, we can look at WEC spacing. Now, WEC spacing, we don't see a 4, 6, and 8 diameter in WEC spacing. We don't see much of an overall difference in the percent wave height change. But if we normalize that by the footprint of each WEC, and by the footprint I mean if we take that 50-meter device that we were talking about earlier, we have a 4 times diameter spacing. Now we're looking at a footprint of over 250 meters area. So the larger footprint does have a larger effect. So we're incorporating these results into a hydrodynamic model because we do want to understand the effects on wave heights, but also small changes in wave heights can have a large effect on nearshore circulation. So we looked at a 10-kilometer by 10-kilometer domain in that area of Santa Cruz. I'm not going to go into too much detail, just given our time here, but we developed a hydrodynamic model by incorporating the radiation shear stresses from the waves, so the forces that actually drive nearshore circulation or rip currents. So we incorporate those into the hydrodynamic model. Then we incorporate tides, winds, everything else under the hydrodynamic model and look at the nearshore circulation. We had nearshore ADCPs, acoustic Doppler current profilers, also other acoustic current meters. In the very near shore and offshore, we also had wave buoys in the near shore, 10-meter near shore to offshore to validate the wave model, so that we had good confidence our model is getting a good baseline. And just in general here, what we're showing is we're showing the wave height propagates into this area. This is about a 2-kilometer wide stretch of the model. We're seeing flow being driven to the eastward, which is common when we have a swell coming from the southwesterly direction. So what do we do once we have all these results to really look at our seabed stability risk, our seabed stability overall? One of the things we can do is we can combine all these lines of evidence like bathymetry, waves and currents, sediment characteristics offshore, and start to develop some metrics that we can look at for the offshore. So by no means do we want to come right into a site, or would we recommend developers go right into a site, develop the fanciest sediment transport, hydrodynamics models in the world. But what can you do to use these tools to actually get good information on what kind of effects can you expect? So we can develop an evaluation criteria. We'd say, well, we know there's zones of low shear and high shear relative to the types of sediment we have out there, just using standard Shields curve. And we can kind of assign those to low risk of mobility to high risk of mobility. And we do all this in ArcGIS. It's a fairly straightforward process. But from that, we can develop a stability risk map to say, okay, we have a baseline. This is what our mobility looks like in a baseline. We can do validation work with multi-beam bathymetry, look at different bottom types. Is this all consistent to validate our picture? And then compare that with our model changes. So what does it look like with WECs in different configurations? And how much change do we expect? So an example evaluation, the top panel here on the right-hand side, shows us our normal sediment stability, or we call it erosion susceptibility, but it's actually sediment stability, where the areas that are the darker brown colors are high mobility areas, and the areas that are the lighter blue colors are low mobility areas. And what we see is in the nearshore, we have higher mobility areas, which is consistent with everything we know about the nearshore transport in the area. In particular, over to the right-hand side of the top plot, we can see this darker area. And that, in fact, it's an area of high mobility. And, in fact, that area is scoured rock reef, so there's really no sediment there. If we go down to our WEC array case, where we have a WEC array in the water, an MHK array in the water, we can see that in the lee where we have the reduced wave heights, we actually have a larger blue area. Now, this may be an area where we can enhance sediment deposition, enhance deposition of fines material, say, and possibly change the transport patterns. In the near shore, we see relatively little change with some reduced mobility in the near shore area in the direct lee. So again, these are the kind of tools we can use, and this would obviously have to be used on a site-specific basis. You know, an example is if we do have scoured reef here that's good habitat for kelp forests, say, and we start to deposit a lot of fine sediment there, that could be a deleterious effect for the ecology of that local region. So overall, a few of the things that we found in our WEC environmental evaluations is that with small arrays in the near field, we see negligible deep water effects. So even though we have up to 30% change in wave height, this is in 40 to 50 meters of water where typically the waves have very little interaction with the bottom, so we have very small effects. So generally we have a very low overall impact to the near-field benthic communities and due to sediment transport. Small areas in the near shore, far field, so looking farther away, looking at the near shore, we do have potential for moderate alteration of those sediment transport patterns. And those are things we discussed. We do see some increased potential for deposition in that lee, but also in the near shore, we do see some reduced near shore circulation. Now again, that is a moderate effect, but that could actually be used as a beneficial, for a beneficial use. Say it's an erosional area of shoreline. Potentially developers could develop WECs, their WEC arrays, such that they help reduce nearshore erosion that we don't want in an area. So in summary, we've leveraged a lot of the hydrodynamic and model development that's been done by Sandia National Laboratories and others. We've taken great advantage of the work that's been done with SWAN wave modeling. And work to enhance these models so that we can develop good methods for understanding MHK devices. We can also use these tools to look at nearshore regions in particular. What we saw is that small arrays of 10 or so WEC devices have minimal effects, almost no measurable effects. You have to scale these arrays very large before we start to see any physical effects at all. But the initial evaluation strongly suggests that adaptive management can be used to really look at how developers and regulators can come up with plans for structuring these arrays such that there's minimal environmental harm and you can maximize power absorption and also potentially come up with other beneficial effects in the area. And with that, we'll open it up to questions. I'd like to thank my co-authors, Kelly and Jesse at Sandia National Laboratories.
And I'd like to make one quick statement that I forgot to say when I was presenting, which is that the SNL SWAN code has been released open source, and it's available on our website and also through GitHub for anyone who's interested in using the code.
Great. Thank you very much, Kelly and Craig. That was excellent. So we do have a couple questions for you guys. So the first is, based on the types of devices and anchoring systems we can anticipate, is there a closure depth beyond which we no longer have to be concerned about potential impacts on nearshore sediment transport and the ocean-beach interface?
That's a very good question, and it's a very relevant question as well. OSU folks have done a lot of work looking at the potential for effects on radiation shear stresses in the nearshore, which of course is going to be your primary nearshore driver, which is another nice screening level approach. But one thing all these studies have found is essentially it's so highly site-specific and WEC and array size specific that it's difficult to have a blanket statement. Of course, you can define a closure depth that beyond that depth, you don't really need to worry too much about transport. But again, as we saw here, we can put WECs in 40 to 50 meters of water, which is well outside the closure depth in this region, and still have an effect on nearshore. Another example of that is our typical northwest swell along the Santa Cruz coast. of course, that hits a WEC array and then goes out into deep Monterey Bay Canyon, so that's zero effect on the nearshore. So again, it's highly situation specific, but that's a good question that needs to be evaluated for every site.
And is there potential for the amplification of wave energy around the edges of device field?
I'm sorry, I missed the last part of your question. Around the edges of what?
Device field.
Could you repeat that one more time? I'm not sure I got it.
Yeah, sorry. So is there the potential for the amplification of wave energy around the edges of device field?
That's a very good question. SWAN is not an appropriate tool for looking at inter-device interactions, but Kelly might be able to comment more on the inter-device interactions and what the effects within that array might be that you could take use of.
Yeah, so the way that SWAN handles wave energy converters is specifically as an energy sink. So if there was going to be some sort of amplification through superposition of radiated waves, the SNL SWAN code is not the appropriate tool to be able to evaluate that. That would have to be done using other numerical methods. So there isn't really a direct answer to that question at this point.
Okay, thank you. So power matrices typically represent the electrical power produced by the device, not the hydrodynamic power absorbed. The difference can be presumed to represent the mechanical efficiency of the device. Did you account for this in your WEC module?
You know, that's a good point, and Kelly probably has more on this as well. The Babaret paper looks at actually power absorbed mechanically by the device. So they modeled the device and looked at the power absorbed, and then I believe they assume 100% efficiency, which of course is not the case. So what we are looking at and what we're trying to model is the actual power absorbed by the mechanical device sitting in the water.
So the framework for how the power performance in terms of relative capture work of the power matrix are implemented within the code, it allows for however the user would define the power. So if the power matrix is in terms of actual power absorbed as opposed to electrical power produced, the code's going to handle that value just the same. So the way that we've implemented the changes and the way that we've described use in the user's manual is that it's up to the user to define what those power matrices are and then accounting for efficiency or, you know, however it is that they see best fit. But I think that it is true that typically a power matrix would be just the electrical power, so it's something worth considering.
Gotcha. Okay, thanks. And so we have several questions coming in for different presenters, so I may just hop around if that's okay with you all. So this next question is for David Wolf. How would you go about best representing the accurate bed resistant values in 3D flow model at Pentland Earth region?
I think that's a very difficult problem, but at the moment we run models with basically a base value resistance, and we think that's probably wrong, but the roughness of the seabed is something very variable. We know how to add in very much the same way that Xiaoqing has described a momentum sink to describe in a very simple way turbines, but what we don't know is an accurate representation of the natural roughness and how that will vary. My personal opinion is that it probably does vary greatly, particularly in somewhere like Pentland Firth, where some places you've got fairly flat plates of bare rock, and in other places you have a lot of fractures and a lot of sawtooth patterns. So there probably is a lot of local variation, but frankly, we don't know how to deal with that at the moment because we don't know how much difference it makes.
Great, thank you, David. So this question is for Craig. What is the directional dependent absorption used when applying the power matrices? Does this vary with device type?
That's a very good question. Right now, we don't have a directional dependence in that. So that's something that, and again, I'm going to punt that to Kelly. That's something that Sandia is working on incorporating into the next iteration as a possible directional dependence.
Yeah, so our first release of the SML Swan code was this fall, and we are currently working on version 2 of the code, where we're including additional functionality like accounting for directional dependent wave energy extraction. So let's say you had a power matrix that was directionally dependent for, a device like an oscillating flap. That's going to be included in the next release, which will be out this summer. However, if there are code modifications like that potential users would like to have, we're looking for suggestions right now. We have our list of code modifications, but if there's features such as, wave directionality or power performance directionality that are of interest, we would certainly like to hear them.
Great, thank you, Kelly. This next question, I believe, is for Craig and Kelly as well. How did you develop power matrices for the WEX you simulated?
Craig, you want me to take this one? So the ones that Craig presented, that was from the Numerical project, the Barbary paper that we referenced. So that was numerical modeling or benchmarking of wave energy converters for about 8 different devices. So we just pulled those from, existing literature as representative devices and power performance values. However, on the validation work that we're doing in the Tsunami Wave Basin at Oregon State for the Columbia Power Array, we're actually using power values directly from developers. So when we have developer data, we use developer data in lieu of developer data, and when we're trying to, provide information that can be released to the public, we use numerically determined power performance matrices or relative capture width curves. In that case, it was the Barbary paper. We've also talked about using other simulation tools to develop our own power performance values.
Great, thank you, Kelly. And this is the final question I'm seeing. Any thoughts about the potential reduction in wave energy from seafloor bottom-mounted devices such as the M3 or the UC Berkeley Fluid Lab types deployed in arrays?
Yeah, ironically, I just met with Marcus Lehman looking at the Cal Wave, or talking about the Cal Wave device. Obviously, theoretically, his devices, or their devices, is looking at completely attenuating all of the wave energy. But they're going to be in 10 to 15 meters of water, so these are different types of devices and have a very different effect on the wave field. So as far as modeling those and incorporating those into the type of framework we're looking here, those are essentially going to have to be special cases. Also with the M3 type device, that's a seafloor device, so they're looking at pressure absorption. So again, that's a very different process than we're looking at modeling here in SWAN. So my thought is SWAN is not likely the appropriate tool for looking at those types of devices, but there may be ways around that, and we just haven't looked at those specific yet.
This is Jesse from Sandia. I think it is worth mentioning that we've talked and used the word impact quite a bit, and we're talking about both positive and potentially deleterious impacts in the near shore. And from some of our studies, just while we have dead air here, it's quite interesting that there has been a lot of positive benefits to reduce sediment transport into a harbor per se, where there's a lot of money spent on dredging those harbors. And from a beach shore restoration standpoint, there's been the modeling implying that there could be an opportunity to establish more sand on the beaches.
Still have about 4 minutes, and I'm not seeing any more questions coming in, but I may just punt this one out for all of you guys, all the presenters, just to maybe try to get a little bit more discussion going. I was wondering if maybe you guys can talk about some of the information or data gaps associated with modeling energy removal out of physical systems, and how you see the best ways of addressing those information and data gaps as we move forward?
Well, I can make a start. I mean, I think one question raised one thing, which is we don't know what seabed roughness is almost anywhere. We have a pretty good idea of a standard value that may work some of the time. But I think that's an obvious data gap. We don't really know what seabed roughnesses are. There are also issues in almost every tidal channel that there is inadequate current data in the public domain. Where somebody is developing a particular channel, they will gather data, but they tend not to share it, and that causes a lot of issues with anybody else trying to calibrate or validate a model. That is very little data out there. I mean, it's quite embarrassing for Pentland Firth that a lot of people are still using one very old data set, which is quite inadequate for validating the currents in their models.
This is Kelly at Sandia. I'll address one of our big gaps on the wave energy side, which is just the lack of publicly available data sets to use for code validation. For example, the data set that we're working with is from 1/33rd scale 1, 3, and 5 WEC arrays that were tested at Oregon State in a basin. There isn't, open ocean data that can be used to check the wave height reduction behind WEC arrays for real deployments, and even there isn't a whole lot of publicly available array data sets from wave tanks either. So sure, we can make changes to the code and we can apply it to existing domains, but there isn't a plethora of validation data sets out there that we can compare the changes with.
Yeah, I think I would echo that as well, that the validation data sets are extremely important, and site-specific data, so we can start out with good baseline models as well and understand the systems even better. And I love David's initial quote, all models are wrong, but some are useful, and that's very true. And it's how we use them is how we determine how useful they are. So we can have the best modeling frameworks in the world, and they can be completely incorrect if the little knobs we turn aren't the right ones and aren't based on good validated data sets.
Great. Well, thank you all. It looks like there's just one last question. Then I guess I'll ask, and then we'll just make the closing remarks and conclude this webinar. So the last question is, how best do spectral wave models address the wave height changes on the immediate lee side of the WEC arrays? This is for Craig and Kelly.
Yeah, I think it gets back to that earlier question as well, is how do we evaluate what's happening on the edge of the WEC arrays and how there might be a potential increase in wave height in a very small area. As Kelly had mentioned, we're looking at energy absorption and energy propagation fundamentally with a wave model like SWAN. What we're not looking at is the nonlinear interactions between the devices, so looking at the reflections and actually creation of small wavelets within the array and what the effects of those are. So if we're talking immediately, like on the order of WEC diameters, SWAN's going to give an approximation or average of what's happening. But again, some of these nonlinear effects can have inter-device effects of addition and cancellation that we're just not aware of. Now, there are models that look at those, but those are extremely computationally extensive models and require a lot of resources to run. So it's assumed that any developer looking at the development of a large array would have to look on that scale for their general engineering design.
One of the things that we considered on the SNL SWAN side for modeling the wave energy converters is that within the SWAN code, you're not going to be able to handle device interaction or any of the radiated waves, but one potential avenue that we're exploring is if the power matrices for an array are defined in such a way that each device can have a different power matrix that is developed based on an interactive body-to-body model, then that would be one way to account for the interaction of devices, but that would be done before it's actually implemented in SWAN. So like Craig said, SNL-SWAN isn't the best code to handle those kind of interaction problems, but there are possible avenues to explore that could at least get at that question.
Great. Thank you. Thank you, guys. Okay, with that, I think we're getting close to the end, so I think I will just wrap up. Hopefully my computer connection hasn't failed and you can see the closing slide there. But first and foremost, I'd like to thank our presenters. You guys did a wonderful job, and thanks for participants for participating today. I'd also like to thank the U.S. Department of Energy for their support for this project and, of course, Annex 4. So as many of you probably know, recordings of this presentation as well as other previous webinars will be posted on TTIS at ttis.pnl.gov. There's also information on TTIS about previous upcoming Annex 4 workshops, so be sure to check those out. The next Annex 4 environmental webinar will be held in April, and will focus on the effects of electromagnetic fields on the marine environment. A date has not yet been determined, so stay tuned for that. And then for those of you who are not on the webinar mailing list, I know sometimes we get emails of other people wanting to join these webinars. You can simply send an email to join-TTIS-webinars@lyris.pnl.gov, and that will automatically get you on our webinar mailing list so that you'll be updated about the next upcoming webinar. And there's the contact information for the Annex 4 team at PNL. And again, I'd like to thank you all, and have a good rest of your morning and afternoon.